Okay, so the model, the verification challenge I'm going to propose is a unicycle platoon of vehicles, which will be coupled by nonlinear feedback. And so the outline of the top is as follows. First, I'm going to discuss the very simple model of the single unicycle, which is three-dimensional, and consider a reachability analysis approach for this three-dimensional case. Then I'm going to extend this model to the more difficult case of a coupled platoon of models, which is 12-dimensional. And then I'm going to contrast the difficulty of performing reachability analysis for the lower dimensional case, which is three-dimensional, with that of the higher dimensional case. And finally, I'll present the verification problem for the higher dimensional case and compare the performance of some algorithms. So first, I'm going to present the smaller dimensional case before going on to the higher dimensional case. A unicycle model is the following set of equations which try to approximate the movement of a robot in 2D space. It is a very simple approximation, where the position is given by x, the x and y coordinates are given by xt and yt, and the orientation with the x-axis is given by theta. So the velocity along the x-axis will be ut times cos theta, and velocity along y-axis will be ut times sine theta, and then we have an angular velocity, which is wt. So now if we introduce angular feedback, then which is a linear angular feedback, which tries to reorient the robot with the x-axis, then the equations look something like this. The feedback, so the angular velocity in this case will be given by minus lambda times theta t, where lambda is the proportionality constant with respect to the angle. Now, if we consider the problem, reachability analysis problem for this three-dimensional unicycle model with feedback for the angular velocity, then we can propose a reachability analysis problem, a simple reachability analysis problem as follows. Take an initial set, which is a box bounding the three-dimensional states, and an interval which contains bounds on the input velocity. And let us say we have some direction vector p, along which we want to compute the projection of the reachable set at any given point at any given time t. So that is given by the formula at the bottom. So we want to compute the supremum of the projection of the reachable set. So this kind of a reachable analysis problem for the single unicycle can solve very efficiently by breaking the initial set. So because the nonlinearity arises due to the angle theta, we can break the initial set along the theta axis into small subsets, very small subsets, and propagate each of the sets. Such an approach is feasible because the dimension of this, the initial set is just 3. I mean, because it's small dimensional, and the nonlinearity only arises because of the theta variable. So this kind of an approach is feasible, and we'll be able to compute very accurate bounds for the single unicycle model using this approach. Now, moving on to the difficult case of a platoon model, the model looks something like this. Now, let us say instead of a single unicycle, we have multiple robots, and we try to control the inter-vehicle distance between the robots and also the lateral drift between of the robots using some nonlinear control laws. An example of such a law is feedback law is given on the right-hand side. So this is the model which I'm going to propose for my verification challenge. So the rate of change of the x and y coordinates are the same as I've shown for the first simple unicycle model, but I introduced a nonlinear feedback for the angular velocity as well as nonlinear feedback for the input velocity for each of the unicycles, which are the UIT. Okay, For the first unicycle, I allow an open loop input of Vt. So as you can see, this is highly nonlinear because there are trigonometric functions as well as inverse functions. Now, if you contrast the difficulty of this problem with the thing of reachability analysis for this Platoon model with respect to the unicycle model, we cannot emulate the same approach that I had suggested for the single unicycle model in the case of the 12-dimensional model, because we cannot figure out how to efficiently divide the initial set in the 12-dimensional model. The nonlinearity in the case of 12-dimensional model arises due to multiple variables, and it will be very difficult to find exactly along which axis to divide the initial set so that we get the best possible approximation of the forward reachable sets. So that is one difficulty with reachability analysis of the unicycle Platoon model as compared to the single unicycle model. Instead, if you try to divide the reachable set along all the axes in order to reduce the linearization error or the abstraction error, this approach is also not feasible because we have a 12-dimensional space, and then we will have to handle the curse of dimensionality. This in 12 dimensions, dividing along all axes would be computationally intractable. So these are challenges associated with the reachability analysis of the unicycle Platoon model. Now I'm going to present the verification problem for the unicycle Platoon model. Let's say I took an initial set of states given with the bounds here, and the open loop input is taken to be a constant of 5 meters per second, and I have 4 robots. So the first property to verify would be to find the maximum lower bound. So the maximum value of D and E, which are lower bounds for the inter-vehicle distance between the vehicles. So we want the, for safety of the dynamics, we would want the distance, inter-vehicle distance between the robots not to exceed a particular threshold. So finding this bound D will allow us to verify whether the threshold is satisfied or not. And the first property is a boundary time property, which says that for between 0 to 5 seconds, and the inter-vehicle distances between all the vehicles are always greater than D. And we want to find the maximum value of D such that this property is satisfied. And the second one is the unbounded time variant of this, which says that for all times, the inter-vehicle distances are greater than or equal to E. And we want to find bounds, the maximum bounds of D comma E such that these properties are satisfied. The second verification challenge is to find the minimum value of D and E's, which are bounds on the lateral drift of the unicycle Platoon. So the boundary, again, the boundary time variation will be like between 0 to 5 seconds. We want to find bounds on the lateral drift of the unicycle vehicles, and the unbounded time property is like for all times, we want to find the bounds. So there's a second property. The third property will be like, I want to verify the convergence of the robots, which means that I don't want the robots to drift too far apart from each other. If the robots drift too far apart from each other, then maybe the communication links between the robots can break. So the feedback laws are designed in a way that the robots try to come together after some time, and then try to and then stay within a bounded distance at all later times. So a bounded time property to verify in this case is to verify that between 5 and 10 seconds, the distances between all the inter-vehicle distance between all the vehicles is always less than or equal to D. And then we want to find the minimum value of D such that this property is satisfied as a verification challenge. And then the unbounded time variation of this is like after 5 seconds for all times, we want to find the minimum value of E such that the inter-vehicle distances are always less than or equal to E. So these are the verification challenges that I propose. And I did not evaluate all the properties, but some of the properties in bounded time, the first two properties were evaluated using well-known approaches. Among them are the Taylor model, the polynomial genotype, and conservative linearization. And I have used a new approach. This I'm going to discuss in tomorrow's talk, which is called intersection of unions of genotypes. And this is a new approach, and there is another approach called single objective optimization. So the Taylor model was implemented in FlowStar, and polynomial genotype and conservative linearization were implemented in Cora tool. The IEO genotype was initial. It's a new algorithm which I'm going to talk tomorrow. It was initially implemented in C++. Then I used Julia, and the results were very good with Julia. I mean, the comparison of the times and all. So that will be discussed later. So from the graphs, we can see that for the first property, the minimum, the maximum lower bound is somewhere close to 5. So this is what I get with the IEO genotype. And the challenge will be to get a bound which is higher than that. And for the second property, where I try to bound the lateral drift, the upper bound is somewhere close to 11. And the challenge will be to get a bound which is smaller than 11. And I haven't evaluated the unbounded time case yet, so that remains open. Maybe the bounds for the unbounded time case and the bounded time case may differ. So the third property I haven't evaluated yet, that also remains open. So in summary, I have proposed a high dimensional unicycle Platoon model with tight coupling between the robots and three properties to verify, or parametric properties for which we want to compute the parameters so that the properties are satisfied. And then I have done some comparisons with the existing algorithms. The possible extensions of the challenge could be like, we can increase the number of robots, and the kind of model I have proposed, it is easily scalable. For example, if I go back to the slide where I propose a model, so this model is parameterized in terms of the number of robots, and we can simply increase the value of n to increase the dimensionality of the model. And so this model is easily scalable. And another thing is like, apart from trying to verify the properties I proposed, we can also try to compute the set of initial conditions, the maximum set of initial conditions that satisfy the properties. This will be very difficult task because the model is high dimensional. So these are possible extensions of the challenge.